In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 1, Introduction, Part 9. Now in this part, we are going to talk about this question. What is the influence of temperature on the material's plasticity? One of the important phenomena that happens during the heating is recrystallization temperature. In fact, recrystallization, as the name implies, means that crystals will form again. As we know, crystals are formed when we produce a material from the raw material. In this figure, we can see indentation pressure plotted against temperature for annealed copper. What is this indentation? Indentation is like a hardness test. It's like this. We have a load applied to an indenter, which is a sharp edge, and this is the specimen. So we push the indenter into the surface of the specimen. If this material is very hard, the indenter will go inside it, will penetrate inside it a little bit. But if the material is soft, the indenter will penetrate more. So that depending on the load indenter and how much it penetrates, we will calibrate this equipment, and we get out of it a hardness number, okay, which depends on the equipment and this indenter. And for instance, like Rockwell C, we say this is 50 Rockwell C. It's a very hard material. So hardness test uses the indenter, but indentation is a process in metal forming or plasticity. Okay, let's go back to our slide here. As we can see, the behavior of annealed copper, how it's changing. Annealed means that we heat up the copper in the furnace to free it from the stresses. So it has no stress in the copper, no remaining stress, and it's a very soft material. So indentation goes like this at temperatures up to about 400 degrees, less than 400 degrees. As you can see, as the temperature increases, of course the indentation force decreases because the material becomes softer. But at some point, I use my cursor here, at some point like that, we see a sudden drop. So something here has happened at this temperature. And then we go ahead and see what happens to aluminum, another material. We see that aluminum also decreases, the indentation temperature decreases with indentation pressure, decreases with increase in temperature. And at some point, about 300 degrees, suddenly we have a drop like that. We have a drop, and then again the same behavior continues. So this drop is called hiatus. It means that a sudden change, okay, a sudden change like that or like that. Also, for different strains also, we have the same behavior. For instance, if we apply 0.5 strain or 0.1 strain, this is true compressive stress. Okay, we will see again at some temperature a drop in the stress. This is due to the recrystallization temperature. What is recrystallization temperature? In this figure, I'm trying to explain the recrystallization temperature. What happens to the grains when we increase the temperature? Okay, in this plot we have shown amount of cold work. Okay, this is the amount of cold work, and here we are showing the different properties like hardness, strength, ductility, and also grain size. What is cold work? Cold work is the work we do at the almost room temperature. Okay, and for instance, when you carry out a tensile test, the material goes through cold work. It is worked on, and we say that cold work because that is at room temperature, at lower temperatures than recrystallization temperature. I will explain about the temperature of cold work later on more. But here we have cold work, and how do we measure cold work? It's like the reduction of area. For instance, when you do a tensile test, the tensile specimen reduces in the cross-sectional area, and that is the amount of cold work we do. For instance, if we reduce the cross-sectional area 20%, we say that we have done 20% cold work. Tensile test, of course, is a very simple test, but also in other metal forming processes like forging, rolling, extrusion, and all kinds of forming processes, we have a reduction of area or cold work, okay, percentage of cold work. Now, here we have done some cold work, and we have increased the strength, the hardness, the ductility, of course, is opposite to this. Usually as these increase, ductility decreases. Also grain size decreases. Okay, this is the original structure with the grain size. Now, here is the cold work. Supposing the cold work we have done here is through the rolling. Okay, we have done some rolling, and as you can see, all these grains have been elongated in that way. So we say this has been cold worked. Now, in this figure, we are putting this into the furnace and increasing the temperature. So here is the increase in temperature. Here again, showing these different properties, how they change with temperature. As you can see, as we increase the temperature, cold work recovers. What does it mean, recover? It means that the stresses which are trapped in the grains are released, okay, at this temperature. This is the recovery phase. Now, recrystallization phase is in this range of temperature. As you can see, it says initial recrystallization. Okay, and here more recrystallization. This is complete recrystallization. What happens here? As we increase the temperature, the atoms in the grains are excited. Their kinetic energy increases, and they move out of the grains. These black things are a group of atoms. They move out of the grains and come at the boundaries where the energy is higher, and they deposit in there. And as you can see, they form new grains. Okay, these are new grains which are formed, and as we increase the temperature, this increases further, and all the previous grains are destroyed, and new grains are replace them. So we see here that these new grains, complete recrystallization happens. In fact, this cold work has been replaced. I mean, it's gone, and we are faced with these new grains. As we can compare this to the initial one, we can see very similar. Okay, they are very similar, and it means that recrystallization means this, that the same crystal that we had originally, they have been produced here again. So this one is exactly the same as that. So the cold work has been replaced, and what happened to the properties? As you can see, it's gone back to here. It's gone back to here. So we got, for instance, a strengths like that. Now we got a strengths here. We got the hardness. It was originally like that. Here again it's like that. So it goes to this original arrangement, and all the properties go to their original values. Also ductility as well, and grain size as well. The grain size is almost the same. Obviously, as we increase the temperature, the grains grow more, and the strength and hardness drop, but the ductility increases. You can see ductility here is almost the same as in here. So this recrystallization temperature is very important, and when we work below recrystallization temperature, if it is near room temperature, then we say that it's cold work. If it is below the recrystallization temperature but more than the room temperature, we say warm work. If it is above recrystallization temperature, then we say it's hot work. In industry, most of the metal forming processes are hot forming, and so most of the working temperatures are above recrystallization temperature. Okay, so this is an explanation about recrystallization temperature. Now coming back to these figures, we can see what I meant by recrystallization temperature. This sudden drop due to the fact that the material becomes very soft, and so we need a less pressure for hardness test or the indentation test or for compression test. We need less stress. Okay. What is the influence of temperature on the material's plasticity? We are continuing this question, asking this question, and here we have a figure which shows stress against strain, but at different temperature. What is the material? Annealed copper at a strain rate of 10 to minus 3 per second. Now I should explain here that when we say a strain rate of 10 to minus 3 per second, it's a very slow process. Okay, so less than 10 to minus 3 per second are strain rates which we call quasi-static. Okay, so this quasi-static means that the strain rate is less than this value or equal to this value. What is the dynamic strain rates? Dynamic strain rates are greater than 10 to power of 3 per second, 1000 per second. And between 10 to minus 3 and 1000 per second is between static and dynamic. So if we want to do the dynamic test, it must be greater than 1000 per second. And if you want to do a static test, it should be less than 10 to minus 3. Of course, it's never a static, it's a quasi-static. It means like a static. Compressive stress strain curves at various temperature, cold, warm, and hot work. Okay, So I just explained to you what cold and warm and hot working are. The recrystallization temperature is the reference point. So if the temperature is less than recrystallization temperature, it means we are working either cold or warm. Cold means near room temperature, warm means greater than room temperature but less than recrystallization temperature. Hot working means greater than recrystallization temperature. Now then, let's have a look at what happens here. At 25 degrees, this is a tensile test or compression test maybe. At 25 degrees, which is room temperature, you can see that we have this curve. As the stress increases, we get some strain, and in order to get more strain, we have to apply more stress. So here we have work hardening. Okay, at cold temperatures, room temperature, we have work hardening, as we call it, cold work. At 200 degrees, which is a warm temperature, 200 degrees, we have some work hardening but much less than this. As we increase the temperature, as you can see, work hardening drops. Also, sigma drops. You see in here, sigma, for instance, for 0.2 strain is like that, but for 200 degrees is much less, and for 300 degrees it decreases. For 410 degrees it becomes much less, because you can see that stress goes as high as this much, while here it goes like that, and it doesn't have much of a strain hardening, while we in here for 0.6 of a strain we have that much of stress, 3.5 times 100 megapascal, but here is much less. For 410 it's about 100 megapascals, and for 610, which is almost hot working, we can see it's not hot working yet, because for this for copper recrystallization temperature is higher, but still you can see that we get a very little or almost no strain hardening, and the yield stress is very much less than the others. As a matter of fact, what I said before, that in industry the working is in the hot region. In fact, we use hot working in industry. Most of the forming operations are carried out above recrystallization temperature, which is hot working. The reason is shown here clearly, because you can see that at 610 we don't have any strain hardening and the stress is very low. But at lower temperatures, for instance room temperature, you can see if we want to form 0.4 or 0.5 or 0.6 of a strain, that's the formation, we have a very high stresses and we have this strain hardening. So because the equipments would have to apply very high loads like that, and also the material goes through strain hardening, and the load goes up and up, and it causes problem for us, for the equipment, for the tools, for the dies, for the rolls. So if we operate in this temperature, at this temperature, then we would have very low stresses, so the size of the equipment is reduced, and the life of the equipment is increased. Also the dies and molds and rolls and all the tools will last more. So that's why we work at temperatures above recrystallization temperature. Here we are continuing with this question, the influence of temperature, and we are seeing a quasi-static compressive stress-strain curve at various temperatures. Here of course we are showing lower temperatures. Okay, this is the room temperature. This is minus 100 degrees C and minus 200 degrees C. As we can see, the effect of temperature is that the material loses its ductility and becomes more brittle. Okay, here you can see the material is so brittle. Of course, the behavior of material is brittle. It breaks there. It has almost no ultimate strength, yield strength, ultimate strength, and the fracture strengths are the same. It's the effect of temperature which causes the material to behave like that. The reason for this is that as the temperature goes down, the kinetic energy of the atoms decreases. So the energy decreases and the edge dislocations find it hard to move because there is no kinetic energy to move them, and that's why it behaves like a brittle material. You can see here is a very ductile material, for instance mild steel, but this mild steel, the same mild steel, if we decrease the temperature, it becomes very brittle.